Hi folks, we're going to take a look at an example of sketching the graph of a transformed logarithmic function. So this is actually page 340, 18b. So they want us to graph this function here. Okay, so first and foremost, before I think about anything at all, number one is to factor out the input to the function. Okay, otherwise, regardless of what that parent function is, we won't be correctly identifying the transformations. So anytime you have some coefficient in front of the x that is not 1, you have to factor it out. Okay, and so it is this format that's going to allow us to read the transformations directly off the equation. Okay, so once I've done that, next step is to identify the parent function, which in this case here clearly is going to be log base 2 of x. So my parent, log base 2 of x. Okay, now there's a few ways you can go about doing this, but what I like to do is to transform enough nice points on the original graph to be able to draw an accurate and fairly good graph. Okay, so I'm going to choose 3 points on this function here. So anytime I'm working with a logarithmic function, I'm always going to pick 1, 0, and now I have to pick 2 other nice points. So I know that 2 to the exponent of 1 is equal to 2, so that means when x is equal to 2, y, which represents the whole expression, which represents the exponent of the base, is going to be equal to 1. Okay, now I'd like to pick 1 point on either side of 1, 0. So I'm going to say that when the y value is equal to negative 1, okay, 2 to the negative 1 is 1/2. Okay, so there's 3 nice points. Now again, you still see me thinking about this function in terms of its exponential form, and you'll probably do that this year. But as you get, if you have to study logarithmic functions in more detail later on, you'll start to really treat these as their own functions. Okay, so now let's recall how transformations work. So if I have a times f at b times x minus h plus k, okay, so a point on the parent function f gets transformed in this way. So anything that's horizontal gets the opposite treatment. So here x is going to be divided by b, okay, and then we're going to add h, and of course the y values are going to be multiplied by a, and then we're going to add k. Okay, so in this case here, what's going to be happening is we have our point xy, okay, is going to become, so in this case here, we're dividing x by 2, and then we're, okay, again, always the opposite, we're subtracting, oops, sorry, made a mistake there, we're subtracting 5 over 2, or we're subtracting 2.5, okay, and then what's happening to the y values, we're multiplying the y values by negative 3, okay, and then we're subtracting 4. Okay, so this is the recipe I'm going to be following. So what happens to 1, 0? Okay, well, we divide 1 by 2, so we have 1/2 minus 2.5, so that gives us negative 2. Okay, and then negative 3 times 0 is 0 minus 4, negative 4. Okay, so the point 1, 0 is getting transformed to negative 2, negative 4. Okay, let's do this here. We have 2 divided by 2 is 1 minus 2.5, so that's negative 1.5, and then the y value is negative 3 minus 4, negative 7. Okay, and lastly, okay, here we have a half that's being divided by 2, so that's 1/4 minus 2.5. Okay, so that's going to be negative 2 1/4, or negative 2.25. Okay, and then negative 3 times negative 1 is positive 3 minus 4, negative 1. Okay, now in your head you should also be thinking, I've got this, flip along the x-axis, and try to think of what the end result should look like. Okay, so now that I've got my points, I'm going to start preparing my graph, and I notice here all my x values are negative, all my y values are negative, and I have to go to negative 7. Okay, so I'm going to draw, I'm going to draw my x-axis pretty high here. Okay, maybe even I'll go up one more, and again I'm going to draw my y-axis to the right, since I'm dealing with all negative numbers. Okay. Now, keep in mind that I've got some pretty small values here, so it might be worth, so certainly for the y values, I'm going to go up by 1. But for the x values, I think I'm going to go up by 0.5. So this will be 1, negative 2. Okay, to give myself a little more space. Now, the other thing is we know that any logarithmic function has a vertical asymptote at x equals 0. Okay, but we're moving this 2.5 units to the left. Okay, so that means that my vertical asymptote is now being shifted over 2.5 units to the left. So let me draw my vertical asymptote here. Okay, so again, helps me draw a nice graph. Okay, so now it's just about plotting these points. So negative 2, negative 4. So negative 2, 1, 2, 3, 4. There's 1 point there. Okay, and we have negative 1.5 and negative 7. So 4, 5, 6, 7. There's another one. Okay, and then we have negative 2.25. So 2 1/4 at negative 1. So somewhere there. Okay. Now this is where you have to be careful because we know what the graph should look like. So I know I'm going to be approaching the vertical asymptote there. Okay, and I really want to show what the end behavior is going to be. I know it's going to be going towards negative infinity. Okay, now this makes sense because the original graph of log base 2 of x looks like this. But remember, one of our transformations is to reflect it about the x-axis. Okay, so it makes sense that now it'll have this decreasing behavior. Okay, so just to repeat here, number 1, make sure you factor out any coefficient of x if there's something other than 1. Number 2, decide on your parent function and 3 starting points. And number 3, determine how those transformations are going to affect the points. And then number 4, draw your graph by first setting up your structure correctly, which in this case here would be the vertical asymptote and a nice scale. Okay, that's it for this one.